Morning geometry students. I think your group wins the prize for the most people who have contacted me by email. And I just shout out to you guys and give you respect that you deserve. Thank you for making sure that everything is working out fine, although there have been people from various other classes checking in and making sure that they know what they're doing. So let's get right to it. Today, you're mostly going to be watching this video and taking notes, and then tomorrow you're going to be mostly working on the assignment. And I do want to make sure that you are continually making sure that you ask questions as well. I did get a question already asked about the homework that was due today, assignment number, what are that, 46. And so I'm going to start off just by answering that. So thank you for asking that question. It was the one that involved having a builder's square. And a builder's square makes a right angle. Okay, and there was a circle involved in it, and it asked for the diameter of this pipe that was being measured. So within that, they also said that there was 1 3/4 inches from here to the tangent. Now, the tangent is significant because when we have a tangent, we know that the tangent is perpendicular and goes through the center of the circle. So all of a sudden, we've got a perpendicular here, here and a perpendicular here. The tangent also goes this way and is perpendicular here. So automatically we have this, and we have a square going on here because radii are equal, and this one would be equal to this one would be equal to this one, and so on. So we've got this square happening here. We have 1 3/4 here, which means there's 1 3/4 here. So since you've got this 1 3/4 and the diameter is all the way around, we would have to take 1 3/4 plus 1 3/4, which is 2 6/4. But we know that we could reduce this. 6 divided by 4 is 1 2/4, or 1 1/2. So 2 plus 1 1/2 would give us 1 1/2. Sorry, my brain got ahead of me. Would give us 3 1/2 inches for the diameter of the pipe. The formula for D in terms of T, well, let's think this out. If we have a variable here instead of the 1 3/4, we still have the square. So when we think about it, the diameter is actually going to equal 2 times however big this number would be. So very good question. Thank you so much for asking it. And I look forward to being able to answer your other homework questions. The third part C, said to justify it. So just like I just explained here in words, if you use your own words to explain about the four right angles and that we got a square and that you have to double a radius, that would be the type of thing that you would write down for part C, and that would be in your own words, however you'd want to express that. But once again, thank you so much for asking, and if you have other questions, please make sure you fill that out when you quote unquote turn in your assignment. So let's get to today's lesson. Today's lesson is about measure and length, arc measure versus arc length. An arc is a piece of a circle. Okay, so it's a part of a circle. This symbol over top refers to arc AB. I believe, Jay, you had asked about that, using some letter initials. You had asked about what the symbol for that was, or maybe it was N that asked about that. I'm kind of not really quite sure, but one of you asked about the arc length or the way that you would symbolize this piece of a circle. So this is it. And the curve part from here to here would be called arc AB. Now, an arc, if it's just with two letters like that, is the shortest arc between these 2 points. And as you're taking notes, do make a sketch and then add to it. Pause me as many times as you need to make sure that you're on the right track. If we put in another point here, point C, that's across the circle, and instead of wanting to go the most direct route, if you really wanted to go around the long way, you would have to reference another point that's on the way going around the long way on the circle. It's still an arc. It's still a piece of that circle. But if you need to show direction, you put another letter in the middle. So arc ACB goes all the way around this way. The minor arc is what we refer to as the small arc, and the big arc that goes all the way around is referred to as the major arc. So we have minor arc AB or major arc ACB all the way around the outside. Notice we've got the symbol here circled D, meaning that D is the center of the circle. And what we can also talk about is that sometimes a major arc or a minor arc, the minor arc being the short distance and the major being the long distance, doesn't apply, because if it goes right through here from B to C, that's exactly halfway. And the halfway marks are the semicircles. Now you might want to designate one side or the other side of the semicircle, so you can do that just like you mark with a major arc, the beginning and end point of the arc you're referring to, and then a point in the middle to show which way. An exact half of a circle is called a semicircle, which should make some sense. A lot of these words just plain make sense. So we have this, BAC is a semicircle, BEC is the other semicircle that goes with the same thing. Okay, so here we have that. Moving right along, I want you to sketch this picture. We have a circle. This is the center of the circle. You have a little line coming out here, a segment. So we've got our central angle here. Remember, it's the central angle goes to the center of the circle and the endpoints are on the circle. So we have a central angle of 32 degrees. And this little M in front of that arc symbol actually refers to the measure of the arc. It has to do with the number of degrees in the central angle. So the measure of arc QR in this case has to refer to 32 degrees. Okay, so the measure of that arc QR is 32 degrees. And that's simply by definition, because the measure of an arc is defined to be the number of degrees. It is not the same as the length of the arc. Like if you took a ruler and you measured somewhere along here, a tape measure, to measure out how long this piece is, that's different from the measure of the arc, which is, in this case, the degrees for the central angle. We can use the things that we already know about angles and their measurements in order to find some of these other arcs. So think for a minute. The measure of arc, RS, is related to this number of degrees right here. And see if you can think of it ahead of me, and feel free to pause as you go so that you can think before hearing an answer. 32 degrees and this unknown number of degrees is going to have to add up to be 180 degrees because it's a linear pair. So in order to find this number of degrees, you take 180 minus 32, which gives you 148. And since 148 degrees is the central angle that relates to arc RS, the measure of arc RS is 148 degrees. Notice that the measures of the arcs are also given in degrees in addition to the angle. So it's a whole different measurement that you're thinking of. Let's think about QRS. It has to go along with the number of degrees here. So some of you have already figured out, wait a minute, the number of degrees when we put these things together is 180 degrees, and you're absolutely right. So the measure of this semicircle, QRS, is 180 degrees. The measure of any semicircle that is the endpoints of a diameter will have to be 180 degrees. Measure of arc QTS, think for a minute, is also 180 degrees. And then the measure of QSR, all the way around here. There's a couple of ways that you could think about that. You could either add 180 here plus 48 and 148, sorry, and get 328 degrees, which is the actual answer. Or some of you might say, well, wait a minute, I know the whole thing is 360. So I could take away 32 degrees. That would also give you 328 degrees. The measure of the major arc QSR is 328 degrees. Measure of an arc, as I said, is very different than the actual length of it, but we'll talk about the length a little bit later. Now, just like we had an angle addition postulate, and so you'd have two small angles and it would add up to a big angle, or we had a postulate dealing with segments with our definition of between, where you had two small segments and they add up to the big segment it makes. Same thing works with arcs. So if I have measure of arc XY plus the measure of arc YZ, that's going to give me the measure of arc XZ. The measure of arc XY plus the measure of arc YZ. And I hope some of you are thinking along and trying to think of these things before they're said. That's the best way for you to learn. Maybe even pause me, interrupt me. That's really cool. You get to interrupt me anytime you want. And then, to give yourself the amount of time that you need to think. Measure of arc YZ plus the measure of arc ZW would be the measure of arc YW. It does happen to be a minor arc. It's slightly under 180 degrees, so you can just say YW. But if you're in doubt and you're not sure if you're seeing it being over or under 180 degrees, it's not wrong if you would have called this YZW, as long as the endpoints are on the endpoints of the arc. And so if I want to take the measure of XW plus WZ, XW plus WZ, that would be the measure of arc XWZ. Happening to be a major arc, you do need to not just say XZ because that would go shortest distance, XWZ. So you kind of have to have a bit of a visual on that. We need to talk about some of the finer points in this. Remember I said that the measure of the arc is different than the measure of, than the actual length of the arc. Okay, two different things. Right here I have what looks kind of like a bullseye. Notice that both of these circles have E as their center. Both of them, if we're looking at this angle, 50 degrees is that central angle measurement. So the measure of arc DC is actually the same as the measure of arc AB. And that's a little bit strange for you to get your head around. The number for the degrees, the measure of arc DC is 50 degrees, because remember it goes with the central angle. The measure of arc AB is also 50 degrees because it matches the central angle. So the measure of the arcs are equal, but the lengths of the arcs are very different. You can see very obviously that this one is a smaller piece. If you wanted to walk this distance, if this was around a circular track and you walked from here to here, it would be a much shorter distance than if you went around the long way. And that should hopefully make sense to you. You can see that you would be walking shorter here than here. The distance that you would walk to get from here to here would be the length of the arc, not the measure of the arc. The measure of the arc is the degrees with the little m in front of it. The length of the arc would use the word length, and you'd be finding the length, how far it is from here to here. If you had to walk it or measure it or whatever your purpose was in doing that. And once again, you might want to pause it here and jot these things down so that you can make sure when you look back at the notes you understand. Today we're going through the notes. Tomorrow is strictly a work day. You're going to be just doing assignment 47 at home during this time. You will not have a video to watch tomorrow. So today is mostly watching, taking notes, make sure you understand, and then tomorrow is a work day to really make sure you understand. All right, we want to think here about some of these things. Now, like I said, you're doing this by writing and pausing. So a circumference, if you remember, is found by doing 2 pi r. 2 pi r is the distance around a circle, also known as a circumference. An arc is a part of that circle. So this is an actual distance. This is a length around. So if you want to think about the arc length, it's a part of the circumference. It's part of going all the way around. So our theorem says the amount of all the way around that you're looking at is when you take the number of degrees, you take the amount of degrees that are in that length and divide it by 360 to get a part of the whole 360 degrees times the circumference. And this will be your formula for arc length. Okay, arc length uses this formula. The measure of the arc is just the central angle. So make sure you're getting that idea down. So here we have an example problem. If we want to find L, L is the arc length, how long that is. We need to use our formula. L equals theta over 360. Well, this is a right angle. I'm given that this is a right angle, which you should all have popping into your head is 90 degrees. So we're taking 90 out of 360. Some of you are even quick enough to say, wait, that's just a quarter. Yes, it is. It's a quarter of the circumference, 2 pi r. So if you're doing it strictly by hand, you can always reduce this to a quarter, cancel out, and get 10 pi. But even if you do not have the TI-83 Plus calculator, what you can do is on a regular calculator is take 10 times 3.14 and get 31.4 inches. That's an approximate value if you were measuring from here to here in inches. So what you're doing is you're going through and you're finding the part of the whole and plugging it into the formula to get how long the arc actually is. Let's look at another one. Here we're given in terms of pi, we're given the arc length, and you're supposed to find theta. So in terms of pi, we're given the arc length. So we're going to once again use our formula. L equals the number of degrees over 360 times 2 pi r. We're going to plug in our numbers here. Here we're given that the arc length is 4 pi. Theta is unknown. We don't know how many degrees this is, but we do know how big the radius is, so we can do this. Okay. Now, there's a couple of different ways to handle this. What we can do is we can work to get rid of the things that are surrounding the theta. If we multiply by 1 over 24 pi, it's going to cancel out the 24 in pi. But remember your rules of algebra, you need to do the same thing to both sides. So we'll multiply both sides by 1 over 24 pi. The pi's will cancel out, so you have less work to do. And 4 and 24 also cancel out because 4 goes into 4, 4 goes into 24, and you get 1/6. There's your theta over 360. Many of you are comfortable with cross multiplying. If you're not, get comfortable with it. 360 times 1 is 360. 6 times pi is 6 pi. 6 theta, not pi, sorry. 1 times 360 is 360. 6 times theta is 6 theta. Even though it's a strange Greek letter theta, remember we make it by doing this. You just divide both sides by 6 like any other algebra problem, and we get that our answer is this is a 60-degree angle. So you use your algebra skills that you bring forward from Algebra 1 and use this formula to be able to solve. Sometimes it requires more calculator work. This completely did not even need a calculator. But if you need to use one, you may. But I'm just saying that your brain is much sharper than you think sometimes. So be confident, use the things that you know about fractions. And if you have any questions, you can let me know and I can give you some things to fill in some gaps and areas that you might be missing. All right, let's look at this. This one has 2 instructions. We need to find theta, and then we need to find r. We're given that this arc length out here is 340 degrees. Okay, so we're going to first have to find theta. If this is 340 degrees and a whole circle is 360 degrees, some of you have already thought, good job, that all you have to do is take 360 minus 340 and you get 20. So 20 degrees is in here. 20 degrees over 360 times 2 pi r equals the length, 3 feet. Then you can either reduce the fraction or you can do whatever other methods that you are comfortable with algebraically. I happen to have reduced the fraction. If you're not good at reducing fractions, you can use a calculator to do that. You can take 20 divided by 360 and then use your math frac button. If for whatever reason that you do not have your TI-83 and you're using your regular normal calculator, you could keep the 0.0555 and just do an approximate value. Then what I did here is I canceled out then the 18 and the 2 and got 9. And I want to get rid of the pi over 9, so I can multiply times the reciprocal. Even though it's got something funny looking in it, you can still use all your algebra skills. So r equals 27 divided by pi. And once again, that's something that on any calculator you have, you could take 27 divided by pi, or divided by 3.14 if you prefer that, and you're going to get an approximate answer, and we can go with that approximate answer of 8.6. I'll allow you to round it to the 10th place, that's just fine. So you're rounding your answer to your 10th place and getting about 8.6 feet, because the original was in feet, so your radius is going to be in feet as well. Another type of question that you could be asked would be to find a perimeter. I know this is a little odd, but we're going to find the perimeter of the sector. Remember, a sector is this whole piece right in here. In order to find the perimeter of the sector, we need to find the whole distance all the way around, so we need to do it in little chunks. If we're finding the perimeter of this sector, the first thing we need to do is find this length. We're going to use that same formula, 110 over 360 times 2 pi. This one does not as conveniently get rid of stuff, okay? Some of it does. 11 over 36 you could do. That's not quite as useful. 36 and 20 can cancel out because they're both divisible by 4. But eventually you're going to have to use that calculator to get your approximate answer at about 19.2. You can, if you want to, take 110 divided by 360 times 2 times 3.14 times 10, and you still should get about 19.2. 19.2 is just from here to here, but we need the perimeter. We need the whole distance around. So some of you have already thought, wait a minute, I have this piece. In order to get the whole distance around means I need to add this piece and this piece to it. Wait, but this piece isn't given. Nope, but some of you are like, wait, but this is the radius, which it is. So since this is the radius, 10 plus 10 plus this number gives you your whole distance around, which is your perimeter. So we have these things. Something like this might be useful if someone were planning like a flower bed and they wanted to have it in a certain shape, and they need to know, like, I want to put flowers every 6 inches or whatever. You figure out your perimeter, and you can figure out how many flowers you need to buy to put in there. So these things have applications outside of just the regular theoretical math. So things like that. Or even I'm seeing possibly even a stage or a place, a zone where you might have some kind of special carpeting on a stage, maybe either for theatrics or even for church, where you've got everything set up, and you're trying to figure out how best to use your space, where to put your instruments. Like, well, what's the perimeter here? How much room is along here if I'm trying to put like a drum kit and things like that? It wouldn't be centimeters, it'd be something else. But you can use these things in lots of applications. We need to talk about the idea of congruence in arcs. In some of the other things like segments and angles, it was enough to say that an angle was congruent as long as their measures were the same. In this case, we have to make sure that in order for us to think about congruent angles, congruent means exactly, or congruent arcs, they have to be exactly the same. So it has to have the same measure as well as the same length. And the only time that happens is if you have the same circle or congruent circles. Okay, so here in the same circle, DC is congruent to AB because they're both 20-degree arcs and they're on the same circle. If we're given that circle O is congruent to circle P, EF would also be congruent to these two. But if the circles were different sizes, then the arcs would not be congruent because they have to actually be the same the same length and have the same measure. So that's just a little bit different than regular angles as far as dealing with that. I had already said all these things. Not all arcs with the same measure are congruent. Not all arcs with the same arc lengths are congruent. Wait a minute, what about this? Not all arcs with the same arc length are congruent. Well, let me just show you some illustrations of these points. Not all arcs with the same measure are congruent because we already looked at this scenario. You've got two circles that have the same measure, but if you took a tape measure from here to here is not the same length as here, so the arcs can't be congruent. Everything has to be exactly the same. Not all arcs with the same arc length are congruent. So if I measured from here to here and I measured from here to here, we might find that with a tape measure, they have the same measurement, but because this is a part of a bigger circle, the measurement, the number of degrees that turn, would actually be less here than over here. So we find out that even though the lengths are the same, the arcs can't be congruent because the number of degrees are not the same. And then finally, our last note on that, all congruent arcs have the same arc length and the same measure. Both have to be the same length and the same measure in order to be congruent. And one last theorem. If you have two chords in congruent circles, the only way that those arcs are going to be congruent is if the segments are also congruent. And the only way that the segments are going to be congruent is if their arcs are congruent. Remember, the IFF means that it goes both ways in this. The only way that the arcs are going to be congruent is if the segments are congruent. And the only way the segments get to be congruent is if the measure of the arc and the angle for the arcs, in other words, the arcs are congruent. So that wraps up the lesson for today. I hope that you were able to understand everything. But if you listened to it and you really tried and you played it back and you're like, I just still don't get it, please make sure that when you fill out the information, the feedback, make sure that you ask the question so I can go back over that point for you again. Tomorrow you're going to be working on assignment 47, so the only thing that you're going to be seeing will be any answers to questions tomorrow. I'll put those up, but you're doing your work tomorrow, and then feel free to, throughout the day, if you have, you're really, really trying, make sure that when you submit your form, when you have completed assignment 47, that you submit your form and then you actually tell me, I need help with this one, this one, this one, so I can prepare something for you. All right? Okay, good job sticking in today. I love you all. I miss you. I can't wait to see you again. And I hope that you really all have an amazing and blessed day.